So we are doing experiment 10. The main objective of this project, this experiment, is to understand the impact of bit error rate on packet error and investigate that impact of error of a simple basic CSMS CD network. So let's see what is bit error rate. Bit error rate is total number of the number of bit errors by total number of bit errors, as you can see the formula. So for example, let's say the transmission might have been a bit error rate of 10 power minus 5, meaning that 1 out of 1 lakh bits exhibits an error, or 2 out of 2 lakh bits, or 3 out of 3 lakh bits. The proportion would be 10 power minus 5. So this BER is an indication of how often a packet or other data unit has to be retransmitted because of this error. So packet error, let's go to the packet error. Packet error is number of incorrectly received data packets received by total number of received packets. So we can derive the formula of this probability from bit error probability. So bit error probability is nothing but the expectation value of this bit error rate. So let's label packet error as P, and P is the bit error rate probability. So P is the bit error rate probability. So 1 minus P is no error, bit with no error. So as the total size of packet is n bits and each bit is independent of other bits, so 1 minus P whole power n is the total packet with no error. So 1 minus P whole power n is the packet with error. So this is how the formula is derived. And so let's see the scenarios. So in the example, we create samples by varying the bit error rates from 0 to 10 power minus 9, minus 8, minus 7, minus in multiples of 10, and we have checked whether the packet output matches the PER formula. So as per the first example, we are doing with 2 nodes, out of which node 2 have default properties, and we are changing the node 1 values as per this table with data error rate as 0 and changing the BER in multiples of 10. So in example 2, we are adding 2 more nodes, and node 3 and node 4 have default properties, and node 1 has the same properties as of the first experiment, and these values should be assigned to node 2. This table, node 2 follows this table, and again we are seeing the output formula. So our main goal is to achieve this table. So let's see. Okay, when the bit error rate is 0, the frames error should be 0, and frames generated should be 4. When the bit error rate is power minus 9, frames error should be 1, and frames generated is 4000. Similarly, when the bit error rate is 10 power minus e power minus 6, then the frames error should be 472 and frames generated should be 4000. Then there are 2 nodes for the hopper. So let's see. So when there is 0, the frames error should be 0, and frames generated is 4000. So when there is error, we are incrementing the error by multiples of 10. So when error is about minus 9, then the frames error rate is 1 and frames generated is 4000. And similarly, if 10 power minus 8, then frames error rate is 2 and frames generated is 4000. and 10 power minus 7, then it is 49 and 40,000. In the last case it is 472 to 47. See, we are clearly following the table. So as per the second table, this should be achieved when in the last case it is 921 and frame generate is 80,000. Yes, this is for, so frame generate is 921 and frame generate is 80,000. When the bit error, so similarly in all remaining cases 96, 80,000, 80,000, so here packet size for the calculation of output table in the first case is 1500 bytes and second or 12,000 bytes. So let's see in that table it is this is the design of hub with 4 nodes. So here we can see that it is 1500. So the N is 1500, and the bit error probability is 1 e power minus 6 e power minus 1. So we should keep the formula in the PER 1 minus PE whole power n. Then we will get this graph. With first case 1 node transmission, this is with 2 nodes and this is 4 nodes. So from the graph we can see that the error rate is increasing, the number of error packets increase. This is exponential because we are increasing the bit error rate in powers of 10. So this is our experiment.